Hello and welcome back once again. So in the previous lecture, we started talking about this phenomenon called dynamic strain aging.
So let's take a quick recap before we proceed. So what we are talking about here, the relationship between the plastic deformation or the dislocation motion with the strain rate. Okay. So right now we are not considering the occurrence of dynamic strain aging. Okay. What we are saying is we are deforming the material under normal conditions when no dynamic strain aging occurs, right? So we are not in that temperature or strain rate range in which DSA can occur. Okay. So under these conditions, what happens is as you increase the strain rate, the waiting time for the dislocations will decrease, as you could see from this particular equation that we just now derived, right? The equation between the strain rate and the time of movement for the dislocations. Okay. So what we are saying is as you decrease this waiting time, the dislocations waiting at a particular barrier will receive less thermal activation because the thermal energy comes in quantum. Okay. It does not come like, continuously as a continuous flow or something. It comes in quanta, and therefore, it as you increase or decrease the time, the amount of thermal energy being received by the dislocation will vary, right? If you decrease the time, obviously the thermal activation which is received by the dislocation will also decrease, right? That is understood. That is straightforward, isn't it? So as you receive less thermal activation, you need to still overcome this barrier that you have, right? This activation barrier that the dislocations have, right? This still has to be overcome, right? And as I said, we have two components here for this activation which helps the dislocation to overcome this barrier. One is the thermal activation, another is the applied stress. Okay. So if thermal activation decreases, this applied stress has to be increased for the dislocations to overcome this activation barrier and move, right? So that's when I said, as you decrease the time or increase the strain rate, the applied stress has to be increased because you have less thermal activation in that case, right? And that is where you can see through this particular equation also as to why the stress increases when you increase the strain rate epsilon dot. So this was under normal conditions, right? When there is no DSA. But now we need to understand what is going to happen to this, this activation and the movement of dislocations when you have occurrence of dynamic strain aging, right? So let us discuss that as well. So now we are saying that this is occurring. That means we are in a temperature and strain rate range where this can occur. Dynamic strain aging can occur. Okay. So now you can consider the same scenario here, and you can apply the same logic that we talked about. That is, you are increasing strain rate and therefore TW is decreasing. Okay, the waiting time for the dislocations at the barrier is decreasing as you are increasing the strain rate. Okay, so under normal conditions, what will happen as a result of that? Just now we have seen. Now let us see when DSA is occurring, what is going to happen. So DSA is the phenomena that occurs due to the pinning of dislocations by the solute atoms, right? So in this case, apart from the dislocation movement, you will also have to consider the movement of the atoms or the diffusion of these solute atoms. Okay, and diffusion is also a time dependent phenomena. Apart from the temperature, the time also has an effect. So it is obvious that if you have less time, then the solute atoms will find it difficult to catch up with the dislocations, right? If the waiting time for the dislocations is less, that means dislocations are waiting for a less amount of time. In other words, they are moving faster, right? So therefore, the solute atoms will find it difficult to catch up with the dislocations, right? So as strain rate increases, leading to a decrease in the waiting time TW, the solute atoms will find it difficult to catch the dislocations. Right, which means the dislocations will be able to move easily because there is no pinning down by the solute atoms, right? In other words, we can also say that the deformation will now occur easily, or it will occur at a lower stress, right? Because if dislocations move easily, you do not really have to apply that much stress for their movement, okay? So as a result of that, the net effect of this will be a decrease in the flow stress. Okay, so again, applying a simple logic over here, like we did in the previous case, here also you can see, why the stress would now decrease. In the previous case, it got increased, but now it is decreasing simply because of the fact that dislocations are moving easily, because solute atoms are not able to catch up with them. So they are not pinned down by the solute atoms, and therefore they can move easily. And easy movement of dislocation means easy deformation also. So therefore, it will require less stress for the deformation to take place, right? So here now, as you increase the strain rate, the stress will decrease, unlike the previous case where there was no occurrence of DSA. The stress is going to decrease with increasing strain rate. Right. So if I want to just illustrate that in the stress strain diagram, that can be shown as follows. So let's say this is at a particular strain rate, epsilon dot 1. Okay. So in one case, if we increase the strain rate, we have seen that the stress will also increase. Okay. When there is no DSA. But with DSA, this is just the opposite. As you increase the strain rate, the stress decreases. Okay, so this is how you can illustrate the same phenomena schematically in the stress diagram also. Okay. And you can also show the effect on the activation barrier when DSA is occurring and DSA is not occurring. You can show the effect of strain rate on the activation. Through this schematic. So this top one is for no DSA condition and this one is for occurrence of dynamic strain agent. Okay. Right, in one case the barrier increases, so more stress has to be applied for the dislocation movement when no DSA is occurring, and when DSA is occurring, on the other hand, the barrier decreases and you need less stress for the movement of dislocations, right? And that you can see in the stress strain diagram also. Now there is a theory behind this also, like we talked about the Cottrell-Bilby theory for the strain aging, for the dynamic strain aging also, as to why those serrations that you see in the stress strain diagram, why do they come, right? There is a theory behind that, and that is what we are going to discuss right now. But before that, let me show you how these serrations look like. So this is a stress strain diagram for an aluminium alloy, which is 5083. That is an aluminium magnesium alloy. Okay, and here you can see these teeth. Okay, these serrations over here across the entire plastic region of this stress strain curve. Okay, so this is what we are talking about here. When the DSA is occurring, the stress strain curve will no longer remain smooth like you would have seen for many other materials. Rather, this kind of serrations will appear in the plastic region of the stress strain curve. Okay. So why this kind of serrations appear? The mechanism, the dislocation mechanism, just now we discussed. But there is another theory proposed by Penning to explain, this kind of serrations when DSA occurs, right? So the theory goes by the name Penning theory. After the name of the person who developed this theory. So what he said, stress strain diagram we have already seen as to how this is going to affect as you increase the strain rate, right? So if it is within that particular strain rate range in which DSA can occur, it will simply decrease the flow stress, okay? So he said this can be also illustrated with a diagram between the stress and the strain rate, because that is what we are talking about here, the relationship between the flow stress and the strain rate. Okay, so instead of plotting stress versus strain like how we generally do, for the deformation behavior of materials, here in order to understand the serrated flow, we can construct a diagram like this between the stress and the strain rate. Okay. And if you do so, it might look like this. So as you increase the strain rate, you know the stress is going to increase as per that power law relationship. But beyond a point, when it enters the strain rate in which the dynamic strain aging can occur, then it will again decrease, right? And as you cross that strain rate range, it is going to increase again. Okay. So this is how the typical behavior will be for a material going through dynamic strain aging. Okay. So this is the strain rate range in which the DSA would occur. This is the lower limit. Let us call that as epsilon dot L, and this is the upper limit. We can call that as epsilon dot U. Okay. So within this strain rate range, if your applied strain rate lies within this range, then dynamic strain aging will occur. Okay. So if you are below this here, or if you are above this over here, then there will be no dynamic strain aging. And stress will increase with strain rate, as you could see in both of these regions, right? So let's say our applied stress is within this range, somewhere over here, okay? So since it is within the range of strain rate in which DSA occurs, under this applied strain rate, you will see a behavior like this where the stress will decrease with increase in strain rate. Okay. So now, in order to explain that, Penning proposed this theory that the stress is dependent on the strain rate. So we can write it in this manner, right? And as the material deforms, we also know that it goes through strain hardening. So strain hardening also is a factor which will affect the deformation behavior of any material, or the flow stress at which you can further deform the material plastically. That will also depend on the strain hardening, right? So therefore, the flow stress can be written in this manner. Where H is the strain hardening coefficient. Okay. So now what we are going to do, we are going to simply differentiate this equation with respect to time. Okay. And let us see what happens. So the left hand side will simply become sigma dot That is nothing but the first derivative of sigma with respect to time, right? And the right hand side will become like this. Epsilon dot is nothing but d epsilon by dt, that is the strain rate. Plus you have this term over here. And we can also rewrite this in the following manner. Right? So this is nothing but epsilon double dot, right? Derivative of epsilon dot. Okay. And this component that you see over here, this d sigma epsilon dot by d epsilon dot, that is nothing but the strain rate hardening, right? Strain hardening is the increase in the stress due to the strain, and strain rate hardening is increase in the stress due to the strain rate. Okay, so strain hardening is due to the strain, and strain rate hardening is due to the change in the strain rate, right? So this, you can say that this is the strain rate hardening part. Okay, and now let us come back to this particular diagram and see what is going to happen if you suddenly change the strain rate from one particular value to another. Okay, so that means we are talking about this change of the stress or the slope of this particular curve. The change of the stress with respect to the strain rate or the slope of this particular curve. Okay, so here you have a maximum at point A and you have a minimum at point B, right? So this will be 0 at point A and B, right? And now if we derive this epsilon double dot from here, we get this particular expression. isn't it? So this term is in the denominator here, right? So the rate of change of strain rate, that means d sigma epsilon dot by dt, will be infinity when this becomes 0, right? Which means at points A and B, epsilon double dot will tend to become infinity. Practically what it means is that this will immediately jump to another strain rate. Okay, so it was here at a particular strain rate, right? It will jump to another strain rate. Okay, so there will be a strain rate jump, okay, when it comes to point A, because here it tends to become infinity. Okay, the rate of change of the strain rate tends to become infinity. That means within a fraction of a second, or immediately, almost in no time, there will be a change in the strain rate, right? So it will jump from one strain rate to another strain rate and come over here to this point. Okay, so now you consider this point, the stress is still same, because stress cannot change or cannot jump like how the strain rate has done, right? So here this is at the same stress, the new strain rate that you have, right? But this is at a stress which is higher than the stress that you are supposed to have at the applied strain rate. That means this is higher than this particular stress. Okay, corresponding to the applied strain rate epsilon dot A. Okay, so therefore, this will tend to come down and try and reach this stress corresponding to this particular point. Let us call that as C, okay, which is corresponding to stress at the applied strain rate epsilon dot A. Okay, so this stress will try and come to point C following this path. Okay, but while doing so, it has to go through point B. Okay, isn't it? It has to pass through point B. Okay, and as it does, as it comes to point B, here also this particular term is again 0, and therefore here also it will become infinity. Epsilon double dot will become infinity, and therefore as soon as it comes to point B, there will be one more strain rate jump. So the strain rate will again jump from here to here immediately. Okay, and come to this point here. But now you can see at this particular point in the second strain rate jump from point B, the stress over here is lower compared to the stress at point C corresponding to the applied strain rate, right? And as a result of that, this will now tend to increase and go to point A following this path. And the moment it comes to point A, the same thing will repeat all over again, and it will again come back to point B, and same thing will again repeat, and that is how this will continue to occur, and you will get those serrations, right? Because this phenomena of going up and then again coming down will continue to occur as long as you are within this strain rate range in which the DSA can occur. Okay, so as long as you are within this range, epsilon dot L to epsilon dot U this going up and down will continue to occur, and as a result of that you will get this kind of serrations, as you could see in this stress strain curve. Okay, so that is how, according to the painting theory, the serrations come in the stress strain curve when the material is deformed in a temperature and strain rate range in which dynamic strain aging occurs. Okay.
All right, so with that, we come to the end of this particular lecture, but there is more to come on this topic. So I'll see you soon again. Thank you for your attention.